just you want to share only one thing, then some specific thing, then that would be okay. And then the importing as well as exporting of the graph and the data in the various format. Let's say you want to export whatever the particular graph in the image file, PDF file, EPS file, and then image to matrix. So whatever the image we have, many times we use various other software. First, you can do this thing, the getting, yes, suppose you have some image, we had shown you some image of maybe some car or something like that, like this one, yourself, and then you can just get the digitized form of the data, and across everywhere, means so you can digitize this whole image and you can convert, and later on you have the data, numerical data, and then you can work on that, and you can do whatever. Okay, and then lastly, we had plotted this 3D surface, actually 3D curve or the 3D data of the surface. So again, I am saying that the importance is the data actually. One, if you are not having a data or the let's say you have just XY column, then you cannot get this thing actually. You cannot get this 3D plot here control. So one has to have the data of that kind, then only one can plot some specific kind of that particular control for any of them. Okay. So today I will discuss some more aspect. Just not that, just one aspect, one more aspect, that is the statistics, and then we will move towards basically the curve fitting actually, because I know everyone would be interested in the getting about the curve fitting, and that is very, very important. Many times we had the data, now we need to actually model it as per the equation available, or you want to get the equation from there. So statistics is simple. The simple one, let's say again going to my simple thing. This is a simple data sheet, and let's say I just select it, and at the bottom I'm getting average, sum, count, the minimum and the maximum. And apart from that, if you want any other statistics, let's say standard deviation and all those, many times we required. So let's say go to the set column value, then function, and then I have the statistics. So you can get average, confidence, count, difference, histogram, kurtosis, maximum, minimum, medium, moving average, slope, quartile, okay, all this skewness, standard deviation, all those things you can get depending. But most of the time we get this thing. Statistics people they require this thing. If for any chance you be requiring this thing, then you can get this thing from there. Okay, so this is the control. This is just a simple simply, let's say, the statistics. Let me see, I have anything on statistics. Yes, I have something. Okay, and this would be important because many times we need this bar graph, bar diagram, or the histogram. Sometimes we say that. Okay, so how to get this thing? So for example, so let me just have some data, for example. So let's say what I do. So I am just copying it from here. So let's say Control C will work. Control C will work. Where is the copy? Yeah, Control C. Now this control copy having two options. One is a copy only and copy with full precision. A full precision means that, for example, let me add one more column here, and I'm adding some number. Many times so we do the calculation and we get this thing. Let's look into that. It truncated itself. I'm getting only this thing, but it truncated. But my digit was this much. But because the lower bound and the upper bound, they have been by default set into this particular column. So that's why this is giving like that. Now, if I just say, let's say this, I am just doing let me, rather than doing this, Control C, and let me just do the Control V. Where is the paste? So I'm getting only this thing. Rather than, let me try. Many times it works. So Control. Just wait. Let me double click it. So this is, so it's showing this thing, but whole number is there. The whole number, whatever. So my point is that each and everything is copied, even though it is not showing to you. Just like here, that is actually the property of basically that particular column. Same thing you can do, just like right click and copy full precision. And let me, I'm just sharing it in this particular column, okay? And then paste. Where is that paste? Yeah, this is the paste. And send. Okay, so both things work. But most of the time when you have a big data, then I suggest, and if you want to have always this kind of require this kind of precision, then always use do not use Control C. Always use Control Alt C. Control Alt C. Another thing which I would like to discuss here. So let us say I copied this thing, only these two cells basically, and now these are row. So I just copied, let's say from here, and let me just bring this paste option. Now this paste is having paste, paste transpose. So any question? Okay. So paste transpose. So now transpose. So this was the row. Now, as we know that in the matrix, the row will be the transpose of a row will be a column. So now, rather than a row, I am getting a column. So many times it requires when you this requires this will be used when we are working with the matrix also. Or let us say you are importing the data from MATLAB also, because many times MATLAB gives you the data in a row many times unless you are specifying it in your code actually. Okay, so this you can just see. Again, I am copying it and let me transpose it. So so now the transpose of a column would be a row. Okay. So this is just a simple, I should cover this thing in the previous sessions, but somehow I forgot. Okay, so let me come to this statistics part. So let me, I'm just copying it from here, whole data, copy. Where is this copy? Yeah. And let me save it. So just look into this, I just copy and save the legends, the long name, they are not coming. The long name, because I just simply did Control C and Control V. So in order to get the whole thing actually, in order to get the whole, exactly whole thing, what I have to do, either copy with this thing, copy including label and row. So let me try to take this thing. Or the best way is that, the very best way is that I should say that I told you to duplicate it. So let me just duplicate it from here, or maybe somewhere in the column, maybe I have duplicate somewhere in the worksheet. Yeah, definitely, because I'm duplicating the worksheet, and I should get somewhere. You can get it actually, it must be there somewhere. So this is the duplicate option. So I'll just duplicate it. So once I duplicate it, so now I need to actually I need to get actually this thing basically this particular plot actually. I need to plot the bar diagram of the histogram. So let us say I am just plotting this thing with these two. Okay. So for that actually what I'll do, I need to let me just delete all these things. Because I'm okay. So whatsoever I need, I'll just play it. Column. So now there are the two things. So two quantities they have been plotted. So many times you can plot the things side by side. So let us say I need to plot only, let us say, for example, this weight of this particular class. So this is what I get, the weight of the class as a function of this thing. Let's say the this is particular name. Okay, so you can get the count. So this is how means you can just plot it. So you can, let's say, this thing. So the two different things you can. Now here you just see in the top their particular counts will always be there. Count is already there. So the both things. Another thing, let me let's say this is, I just put it as X, and this is height C. So now this is as a function of age. Now later on you can just play with that, the width and all those things, spacing. So you can just decrease it. You can just manipulate it. It's just enough. So this is just the statistics. Now, the important thing is that the curve fitting, which we will be discussing here. So let me open a new file for, here is the new, this one. So again, I'm just getting the data. Sample, then this would be curve fitting, outlier. Okay. So you have somewhere data. So this is what the data I have. So now I need to plot, let's say first one is the linear plotting. Okay, so there are basically the two kinds of the plotting, linear and non-linear. And non-linear is a very big. So you can have parabolic, you can have elliptical, you can have Gaussian, Lorentzian, any other kind of exponential, logarithmic, various kinds of things are there. So let me just plot it here. So this is the data. So this is the graph, and now I need to plot it linears. Okay. For that, the important thing is now this you just see this analysis window. This window, this menu option will be available for both, even for the analysis, even for the graph both option. Okay, which means that you do not need to plot the graph for basically fitting it. Okay, as far as you are doing the 2D fitting. But if you are going for the 3D plot, and let's say you have the 3D curve and you want to fit it to 3D curve, then then you have to go only with the sheet, not with the graph, because origin will not support. Okay, so this may be some sort of thing which they have kept for the actually. Otherwise, the system will take more memory or something like that. Okay, so for the 3D plotting, data fitting, one has to go with only sheet active. So now in these two cases, which one is active? The sheet is active. You can say that this is somewhat more grayed as compared to this. Now when I click it, so now this would be grayed out. So this is not activated, and this is the activated. So analysis. So in analysis, you will have many options. So statistics, this is the descriptive statistics which we have actually seen. Some sort of, okay. So statistics on the column or so. So we will come back to more about the statistics at the end. Now this fitting part which we can have. So linear, so fitting, then linear fitting, you have the many things. So fitting and then this open dialog. So open dialog, so you can recalculate it manual or auto. It's a meaning I will tell you. Basically, you can, whenever let's say you change any parameter and you want to see what would be the consequences of that onto your fitting. So for that, auto will automatically do the new fitting. Manually means you have to click some button, you have to invoke some command, then it will do the actually. You have to trigger some command, you have to trigger some switch, then it will do the actually recalculation point of view. This input range, when this is giving you the graph, okay, so you can manipulate it, you can change it, which data you want. Even if you can just say that no, I want only 5 data to be fitted, so you can just get it from here, just like here. So, okay. Then this fitting option, instrumental, the residual, this residual and all those things I will tell you in a bit. I will take a bit time. Okay, so let's say I'm going with the most of the default settings and I get this straight line. Let me choose it. I hope this. So now, so this would be a best fit line. Linear regression. Okay, y is equals to a plus bx. You can just look into this. Y is equals to a plus bx is there, and this residual value is there. Pearson R coefficient is there. If maybe some of you have taken any courses of statistics in graduation level, undergraduate level, you might be you might be at least know these words. What is the residual? What is the R square value, Pearson number? And most importantly, we are just worrying about this thing, y is equal to a plus bx basically. I'm interested in that. So now intercept value is this much, slope value is this much, and this is the error. So I can say that intercept would be 0.68 plus minus 1.22. Slope would be 0.96 plus minus 0.23, like that, depending on how many significant figures you want to have. Okay. So this is the just a linear fitting, and you can do it. But I usually ask at least from let's say undergraduate people or the MSc student how Origin or any software, not Origin particular, you can do this thing in numerous amount of numerous different softwares. You can do it, but how that particular software did this kind of fitting, you should know that at least just linear fitting actually. Okay, so please try to understand that bit. Okay, so basically you can just get it the value of sigma y, sigma xy, and then with some linear fitting, and from there you can get the centroid of this particular data point, and then you can calculate it. Okay. So now this is the linear fitting which I have, but let me close it. This is the table that has the data. Now, as soon as fitting completes, I get two more sheets here. So this one particular sheet is having the various parameter which I got from the fitting actually, the statistics, the interceptors, the parameter value. Okay, and this NOI is some sort of a parameter which statistics people they use for to get the confidence of fitting, to get the quality of the fitting. Okay, and this is the fitting curve, and this is the residual. Now, what is residual? Can anyone tell me what is residual? Or you can just raise your hand if you know. Anyone know what is residual? At least by the name, not just related to this origin also. Just residual. What do you understand by the word residual? Residue, at least in residue word you might be knowing in complex integration. No. Okay. Surprise me. Okay, no issue. So so I'll just no, not I was working with this sheet. Okay. So and this particular sheet is having the fitted data. Fitted data means let me this red line. This red line must have some data points. This red line must have, these are the data points you can just see. Okay, so the value of those data point is given by this thing. So let us say if I just plot it here, then I should get a perfect straight line. This is the straight line. Okay, so basically now I have the data corresponding to this straight line. So you can plot it there. Okay, now if I'm looking into this my this curve. Okay, so let us say I did the experiment and I know that my what would be my range of observables. So with that actually I decided that, or I know that these point and these 2 points, they are very far from my observation, and there must be something wrong in the observations. So either I can do the repeat the experiments, or I can discard or mask these two data points depending on that. So if I want to do that, so what I'll do, I'll just right click on it. Let me right click on this mask, and then disable masking, let's say, then enable masking. So let's say data and this mask data points. Data, so I just went to this data and then mask data point, and then I have to now that this you just see that the cursor changes its some sort of symbol. Now I have to double click on that, whatever the data point I would like to mask. Now one more thing, look into this. Please try to remember at least this thing r square value. Uh, Adjusted R square value. This is 0.63. Let me, 0.63, and the slope and all those things. You please remember actually. Okay, or let me just write it somewhere. So R square is 0.63, intercept is 0.67, something slope is 0.96. Just looking into these three numbers. Okay. Because what I'm saying that since these 2 points are, let's say, means very far from my observations or my prediction, then I'm excluding these things from this data fitting. Okay, now I will do the replot or the basically redo the curve, this curve fitting. So I'll go to this particular link. You can just see this is yellow color, some sort of unlock symbol is there. If it is locked, then you cannot do the recalculation. If it is unlocked, then you can do the recalculation. Right click there, sorry, uh, left click there, Okay, now recalculate. Left click there. Now, if you remember earlier, I said that there were a different option, manual, auto, and if I had this auto, then it will do automatically this thing. But since I just put the manual, so I have to do this recalculate. It did this thing, and now look into this. Now the residual, which was earlier 0.63, sorry, I was not looking into. I was looking this R square. R square earlier was this was 0.63. Now it is 0.97. Intercept, which was earlier 0.67, now it is 1.09, and the slope is 0.92, like that. So now things have been changed. Okay, now how do you know that which fitting is good? How do you know that which fitting is good? So for that, I'll take more time, but just let me know that any means in confusion or any doubt so far, the plotting of the graph plotting and the masking of the data and the replotting. And you just see that whatsoever the data I have masked, they have been highlighted in the graph also. They have been highlighted, sorry, in the data sheet also. So these 2 points, they have been ignored. You can just think about that. Okay, so let me go back to this slide. So this is what the graph fitting. So now the residual, I can just show you again this graph, this linear fit. No, here, because I asked you the residual, no one has spotted. So let me double click on it. So this is the residual. So residual means that, so this is the zero line, okay, and these are the data point. These are the data points. Sorry, not the data point. The value of the residual. Now, what is the residual? Is that suppose I want to get the residual of this particular point. So this particular point is deviated from this particular line. Deviated from this particular line. So what we do? We just drop a perpendicular from here to this line. So this is basically a distance. This would be some sort of distance. Okay. So each point is having some sort of distance. Now, some of the distance would be positive and some of would be negative. Let us say if I'm making these points is above the line, so this is positive, and these points, they are below the line, so they have the negative. Okay, but we are taking the square of that, so that's why it will give me the positive number always. So the square of these distances, that will actually represent in this the R square, the residual basically, and the square of the residual, and this is 1.16, which is given in this particular table. And now imagine if these points are very close, to this line, or let us say exactly on this particular line, then the value of this squares would be minimum, or the close to the zero value, close to the zero value. So this particular graph tells us the quality of the fit. Many times we have that this R square number, this should be close to 1. Its value would always be 0 to 1 in between. Okay, and the more towards the 1, that would be the high confidence of your, or the better quality of your fitting. So many times people say that, and we used to say that the more number of nines, let's say 999, 49, 59, the more number of 9, it signifies the better quality of your fitting. But rather than that, so that would be an option which that would be a number which you can just judge from the let's say front panel, and but this would be a more comprehensive way to understand that. So this number, this should be as small, and here also you can find out which data is deviating more from your model, from your fitting actually. So let's say if I just say that this number or this observation is almost very close to your basically take data point. And also you need to look into this number also, so the tolerance also. how much the deviation you are affecting. So let us say, if someone can say that, let us say I have just let's say -5 to, let us say, +5. If I just plot it like that, then one can say that no, now things are very much close to each other. So which means that if I am having the tolerance of, let's say, ±5, then in that case I can say that this is a very small number. So again, it depends on your observation actually, and whatever the experiments you did from where you got that particular data. So this is just for the linear fit. Coming back to here, so this R squared value, this is almost always 0 to 1, now means 0 to 100%. And in ideal case, that this should be the sum of this. So now there are the two things: the R squared value and the sum of R squared, so the residual square. These are the two different things actually. Okay, so this sum should be means it could be 0. So smaller the value, better your fit actually. So for that, actually, the various parameters which people are using in this kind of regressions actually to interpret the result. So basically, for the linear fit, this actually comes into picture. The Pearson number, the Pearson coefficient, this value should be actually, it goes to from -1 to 1, and more towards the 1, either +1 or the -1, you have the better modeling. Okay. More towards the, let's say, -0.99 or +0.99, so which means that you have the better fitting as compared to, let's say, R is equals to 0.6 or 0.1 or like that. Okay, so this residual sum squares, I have explained that, and for the perfect data fit, this value will be 0 actually. So smaller the value, then you have the better the result. And why it is smaller, I explained that also. I tried to explain actually. Similarly, the factor, there are some square root of chi square. We will see that number also comes to be. So this number actually, typically this value should be close to 1. Okay. If it is more than 1, then which means that your basically model is some sort of overestimating your observations actually. And if it is very much less than 1, which means that the underestimating. So based on that, actually you can play with your parameters and you can try to get the good fit. The R square, the COD is basically the coefficient of determination. That means that is again statistical quantity. So it should be 0 to 1. Okay, so the larger means more close towards the 1, you have the better result, better modeling of the result. So similarly, the adjusted R square. So this time you are actually adjusting the R with whatever the R square. So here we have the residual. Then we just take the square of that. So that is the R square. And now this R square is adjusted with some whatever the prediction you are making. You are giving to your particular linear fit. It's a regression actually, whether it's linear on the or the non-linear value. And if it is actually basically depending on the number of predictors which are available in your fitting, so this value could be greater than 1 or less than 1. So I always, at least for my means, you can say that it's my advice, you always try to look into where is that this currently, this residual. So this will help you to identify even which data point is giving you the more error, and whether the exclusion or the masking of that point will help you in both way actually. It should not change the physics. It should not change the theory, whatever you are proposing or you are getting through that particular model also. Okay. So this is basically the linear fit. I hope this is clear to everyone. Now this is the non-linear fit I'm coming to the start. So for maybe I have the non-linear fit also. So this is turn, this is statistics, outlier. Okay, so this is the non-linear. So from where I get this data? Yeah, this is. So let me close it everything. Okay, so again open it. Open the data. So for 15, then I have the Gaussian. Where is the Gaussian? Yeah. So this is the Gaussian. I have some data. Okay, Gaussian data. Okay, so you can plot it every. So now look into this. This is some channel. This is the amplitude, and this is the error in amplitude. This is the error in the amplitude. So I'll just plot this amplitude as a starting point. So this is what I have this error. Okay. Now I would like to plot error also. Many times you might have seen that people had plot the error. So for that actually we need to make this column as an error. So set as y error. So I just make it as error. Look into that. It changes this thing. Now there are two ways I can plot this graph into this graph number 2. The first way is the very first way which I had given you previous session, that the plotting of multiple curves. Okay. Or the another way is that I just select it. Just look into that. The arrow is like that. The cursor here, the cursor is like this. Here, the cursor. Now, as soon as I'm going here, the cursor becomes some sort of downwards arrow. As soon as I am looking going towards this bottom of this, the cursor becomes like that. Now I just take this thing. Okay, it's not. Yeah, I need to actually drag it. Yeah, just so it would be like that, like that. Okay. So now it remains like that as I plot it. So now the same thing is there. So this might means you can do it from the other, but this is some sort of a shortcut to that. So now I have the error. So you just see that the error is also keep on changing. Many times people say that the error throughout the experiments is remains the same, but it should, as an experimentalist point of view, the error will always change from data point to the data point. Okay, so you can just look into that. You can even see the magnitude also. The error is keep on changing. Let's look into that. Here the error is 7. Okay, and here the error is 1. Let's say 732. Okay, many times you just see that the square root. So it's just a error root is in this particular table. I just created this table like that. The square root of that. Okay, so this is what now I need to plot it. So as I said that it is a Gaussian, so that's why I will be plotting the Gaussian plot. But before plotting the graph, you should know that what function you will be utilizing that. So now again, now not linear fit, no polynomial fit. Now polynomial you can do with the polynomial of 2 degree, 3 degree, 4 degree, 5 degree, 7 degree, like self. Okay, like 5 degree polynomial will start with a5 y x to the power 5, a4 x to the power 4, a3 x to the power 3, and so on like that. Okay. Now non-linear curve fit. So always remember non-linear curve fit. Now in the non-linear, I have the two options: non-linear curve fit, non-linear implicit curve fit. Implicit means you are not too much sure about the function, but you know the basic trajectory kind of function. So you start with that actually. So this is some sort of explicit curve fitting. So open dialog, and shortcut is Control Y. So many times you can just do it Control Y, you will get this thing. So please look carefully. So there are various kinds of category of the function which you have to use. The origin basic function, if you just select it, the corresponding the function in this directory, they will open it. Beta, hyperbole, exponential, decay, hyperbole, all this thing, Gauss, and then exponential. So another function. Okay, maybe some of the function will be common. Okay, now I know that this is some sort of peak function. This is, you can look into that. This is some sort of peak. So I'll go to the peak function. Now all the function which is related to the peak, they will come into this category. Asymmetric to sigma, beta, CC, extreme, Gauss, Gaussian, Gauss amplitude, Gauss modification, by Gaussian, DS, gliding in Laplace. Okay, many times Lorentzian. Okay, so these are the various functions are there. So let's say I'm going with the Gaussian function. This is the Gaussian function. Okay, it by default it fitted. Okay, okay. Now, so this is what the function selection. Now the data selection. The data selection means that which data you want to have. So you can just get it from here. You can change the range. You want C to be plotted. You want B to be plotted, like that. So you can change that also. Okay. Row you can manipulate with the row. Yeah, row is here by row. If you want to plot, let's say if you want to plot from here to here, so you get the data number corresponding to this, data number corresponding to this. So let me start with, let's say, data point number 25 to, let's say, data point number let's say 50. Right? So it is, so this is plotting only this much. Okay. So one can do with that. Selection, right? I mean selective fitting also. Okay. Then fitted curves, whatever the data is fitted after fitting, this red color data, that is the fitted curve, what you want to do with that. So you can go with that. Find XY, advance, output, and all those, going with the default things. Actually, you can please try to explore all these things. Now, this is the function, this is the graph, this is the equation of that particular Gaussian. Okay, so this is the equation which this particular function, which is inbuilt, it's given there. You can manipulate it also, but I suggest do not manipulate this inbuilt function. Try to add the your new function. Okay, so this is the parameters. These are the parameters which you can say that the function depends on. The parameters, you can say that y is equals to mx plus c. Now the two parameters which are m and c, these are the two parameters which you will get after the fitting. You remember, after the fitting the data, I get the intercept and the slope. So these similarly we have this y naught. Y naught is some sort of the baseline, basically. X is the center of this particular peak. A is the amplitude value of this particular peak, and the W is the full width of maximum of that particular peak, which you can get it from here. Okay. Definitely on the x-axis, that is the independent variable. On the y-axis, we have the dependent variable. Okay. The bound, now the bound, you can just set it, whatever the value you have, you can set that these values should be positive, these values should be negative, this value should be 0. So these kind of the things for the like better estimation and trying to save the time of the fitting, you can just get it. Okay, you can just make the bound, the lower bound and the upper bound, all those things. So I'm not doing that thing. You can even fix these values that I want to fitting of this with, let's say, x is equals to only 26. Okay, so you can do that kind of the fitting also. Here you will get the residual at this particular point, whatever the value of the residual. This is the formula of the Gaussian. This is the simple curve, so you can get an idea about this thing. Now, this formula and this simple curve, you will get only for those which are inbuilt there, which are inbuilt functions. So if you create a new function here, then you will not get the sample curve again. This is a message which is very, very important. Whatsoever you will be doing, it will be reflecting, prompting some message here. This is the function file where the function is there, and that is written in the C actually. That is written in the C and some laptop, a lab talk actually. And these are the parameters which will help you what you are doing, how you can manipulate this thing. So I'll be just looking into this message, and I have seen that the fitting is not good. And this is the function, and this is the basically you initialize the parameter. This is the simplest thing. This is the chi-square. You can calculate it. This particular thing will do the one iteration, just only one iteration. So one iteration is done. You get the chi-square value like that. The COD, the R-square value is this. This is what, and you change this value. Now look into the values has been changed, and these values have some sort of error is there, and how much is the dependency is there. So dependency has to be there. If the parameter is not having any dependency or very low value of dependency, then what you can do, you can ignore that parameter. I mean, that parameter is not affecting your fitting actually. And this option, this is the, if I just click it fit, then what it will do, it will do the iteration many times as long the fitting is done, and basically whatever that tolerance criteria that is given in this here, tolerance criteria, if I remember, that is 1 into 10 to the power minus 9 that is given there. So let me do it. Yeah, so fit is convert. So I have just clicked here. So fit until converged. So it will do the various iterations until and unless the fitting is converged, or the tolerance criteria of this much is reduced. It is reduced. Many times, Origin will do. I think by default there are only 200 iterations are there. So by default it will do only 200 iterations, and if it is not getting this much tolerance in chi-square, reduced chi-square, then it will say that fit is not converged. Then you have to redo again. So fit is converged. This is the message you are getting. Chi-square value is reduced chi-square values comes out to be this. with this much, which means that the previous two values of the chi-square, they have this much difference. They have this much difference. Okay, and so look into this R square value. So this is better as compared to this much. Earlier it was 9423. Now this is 9444. So this is more as compared to this. So this is better, and total iterations have been taken 5, and these are the values. Okay, let me, and if you just OK it, you will get a result. Now, one more thing which I want. Many times you want that this is the fixed value. Let's say I just want this, for example, y naught to be, let's say, 5, for example, and I want that this should be fixed. Means now it is not going to change throughout my fit. So if it is not varying, then the error would be 0. The error should be 0. So let me do this thing. So error is 0, dependency is 0 because I fixed that thing. So there is no dependency, and accordingly other parameters has changed. You just see that the graph is almost same. Okay. Now look into this number. This thing. So earlier it was 99444 and this was 9329, and it took 10 iterations, more iterations actually. Okay. So though fit is converged, but the R square value is somewhat increased as compared to that. But one can say that there is not that much difference. So let's go back to this residual. Now look into this residual value. Okay, and now I am just doing this thing. Means I have removed this fix and okay. So you will be finding that as here the difference is not that much, so you will not get a very magnificent difference in this particular curve. I will give you an example where we will have the good amount of the difference in this particular curve. But in that scenario, one has to go with this value. And let's say I just OK it, so it will be done. It will be pasted here, and the data is plotted here. So here these are the value, and this is the fitted value. This is the fitted value. So when you want to plot the graph, actually, so you have to take this is your fitted curve, and this is your actual curve. Okay, so one can say that this is the black squares. This is the data points. The bar lines, these are the error, and this red light is basically some sort of you can say that no, not some sort of. Basically, it is the fitting, and one can say that at the tail, at the shoulder of this particular peak, the data points, they are actually deviating from the model basically. Okay. So any doubt or anything which you want to discuss here now? Okay. So let me go back here. So this we did it. Control Y is some sort of shortcut to invoke this nonlinear fitting. And let me go to the new sheet and just here. Yeah. Now this is some sort of the data which was taken by me. This is the resistivity, means now more towards the physics actually, but no physical concept. Just it's a resistivity as a function of temperature, which is plotted for the 3 different samples actually. And the inset is showing the same thing actually, but only up to some limited temperature, let's say from 5 Kelvin to this around 80 Kelvin. Okay. And you just see that the fitting is done with some 3 different kinds of equation. We are not worrying about the equations, but 3 different equations I did take. Equation 1, 2, and 3. Everywhere equation 1, 2, and 3. Okay. But if I look into this curve actually, so more or less in this particular, let me take this pointer. Okay. More or in this particular region, the fitting values they are taking more or less same. They're following the data actually. But here in the lower region, low temperature region, look into that. Okay, the fitting is not taking that. I mean the model, all the equations they are not taking. At least this particular red curve, this is not taking that. So I have plotted this residual curve, the same thing for all this. Not plot. I even get the data, and you just look into that at the low temperature region. At least for this sample, this red curve is having more deviation. The red curve is having almost every time. So here it is having deviation, here is deviation, here is deviation, here is deviation. This red curve, which means the red curve or red equation, the equation corresponding to equation number 1 So here that equation 1 is somewhat that is around almost flat or close to 0 up to the same scale basically. If I'm just comparing this okay, the same scale. So except the low temperature, this is some sort of or acceptable, you can just say, but not a good, very good, but acceptable. Similarly, for the green, which is some sort of another equation number 2, that is having a good consistency from low temperature up to high temperature, but around this 90 to 100 or something like that, this is having a deviation. A similar trend is getting from here. Okay, so with this kind of analysis, one can just if you just look into this number, let me show you this number. Just go with this numbers, the R square value. In everywhere, I have the good numbers. You can just look into that. 99 like that. So everywhere we have that. Somewhere we have the 999 also. Somewhere we have the 999. Okay, 999 into this 999. Sorry, 999 4903 You can see very small difference. So I can say that both are the fine. No, but I have to go with the residual also. So then only I can comment on the quality of the confidence of the fitting. So this I just wanted to point it out here. Okay. So now more about this fitting. Here I will take basically in this particular slide, I just take the 3 different curves. Okay, that the experiments were done, and now I need to do the simultaneously the fitting of all these 3 curves, batch fitting, you can say that, simultaneously fitting within the same range. And I need to compare some parameter which I'm getting from the that fitting. And I would like to say that then I have to comment on that which fitting is good, which fitting is fitting is same, but which is sample or which particular data is more towards my fitting model or not actually. So this is actually the global fitting or the batch fitting which we can just do from there. Okay, so let me again. So for that, actually, I need to plot some data. So let me close it. Open. Control K. Curve fitting I have there. Then exponential decay there. Yes. So in exponential decay. So I have as a function of time, 3 observations has been done. Okay. So it could be photoconductivity, photo response, or any other thing. Okay, so not worrying about that. So let me, I have this data. So this is the data I have. Okay. Now I need to actually plot. So I just plotted it there. Then I need to select whatever the data I would like to have. So data selection is there. So I need to select some specific range. So this look into this toolbar icon. So I can just click. Then the selection by default is selection on active plot. Active plot means that now I have the 3 plots are there. You just look into there, and in the 3, the active one is just only one. This one. If I just look it there, then the second one would be active. But here I need to select the data for all the 3 ones. So for that I have to just everywhere you just see that there is small triangle icon is there. You just click it there, and you get the 2 options. I am looking selection on all plots. So basically, let's say I'm just selecting it from here 0.4 to let's say 1 and that or whatever. So now this time you just see marker has been put, and you can see this horizontal marker here, here, here. So which means that all the data corresponding to all the 3 curves has been selected actually or activated. So what we have to do now, the control Y, or let us say analysis. Fitting nonlinear curve fit, open dialog. Okay. Now this would be actually exponential, so I'll just go with this. Exponential is there. Experimental decay. Okay, so depending on your equation, so this is I'm just taking the equation. Okay. Now the data selection. You just see that the 3 data have been given. Now how many data points? 42 to 99. So for data number 42. Which would be here, to data number 99, which will be here. So these data points are there, and it is given here the 3 different range. So 3 different data have been given, and you look into that, the red line, the green line, and the blue line. So they have been coming to picture, which means that the first kind of the fitting is done. Now, and look into this multi-data fit. So it's saying that you are doing this multi-data fit. So from here, remember this thing, you have to do this thing global fit. So basically all the three things would be global. Okay. And so any other thing? Just look into that, the function, all those things, data selection, curve fit. So all, I'm just taking that this is your equation. Okay, you can get it from here equation actually. This is the equation, and this would be the some sort of the curve. This would be the actually your basically parameter. Now, look into this formula. What, how many parameters which you can get from here? Why not A1 and T1? So basically the three parameters which you will get from here. Now there are three different equations, which mean that 9 parameters. Look into that. These three corresponding to first graph, these three corresponding to second graph, and these three corresponding to third graph. Okay. Now this T, basically 1 by tau, 1 by T is some sort of time constant. So this would be some sort of the time constant, and it would be actually depending. It should not depend on your material basically. Okay. I mean, it's again, it depends on your experiment also. So you can do that thing, a share. So this thing was not earlier. So what you can do, let's say I'm just share this T1. So now this T1 would be this time constant basically, or the decay constant would be share. It would be shared for all the three curves actually. So what I did from there, I made this thing common for all the these three different fittings. So you can share all, you can do the sharing of this particular constant also. Okay. And then just what you do, just go to the message, let's fit it. The first fitting is done, and then fit until, so it took almost 97 total iteration. The fitting has been done, fit is converged, 1e minus 9 is reached, and 9968, this is the basically the your R square value, which is comes picture. Okay, and you can go, let's say the residual. So this is the different residual, red, blue, green for the different colors actually. Okay. And let's say okay, so you will, so basically you get this fitting parameter, and now you can just change it. Let's say, means you can do this kind of formatting, coloring, and all those. So not going into detail of that. There is a data sheet. So if somewhere I'm not getting the data sheet, what I'll do, I'll just click it there, workbook. Now it will come up. Okay, so this is the data sheet I get. So I'm going to the result. Okay, so you just see this. Yeah, this T1 value. So this is same because I fix it. So this is same for all the three curves, and they have the same similar because same is there, same. But you can do this thing. You can have the various thing, and then the different value will come into picture. Okay, this one. Okay. Go to summary. Then summary. This is the summary thing. So you can analyze this particular data which you are getting. So you can do the summary, then create a copy as a new sheet. So which means that the summary will be making as a new sheet. So now this, because you need to plot a graph also. You need to plot a graph. And you just see that, let me, so you just see this is the hash is written there, which means that the column width is small and data is somewhat more. So for that, actually, you need to double click on it, or you need to just expand it. But this problem has been overlooked. Also, this problem has been removed in the current or the recent version of Gaussian. Okay. Any Santilata, you want to ask anything? So, so I get this particular data. So now what I'll do, I'll just I need to plot actually this thing. Any parameter, fitting parameter which you want to have. So let's say I want to plot this D parameter. Basically, that was the A1. A1 is the amplitude. So I need to compare the amplitude of all those three with this thing. Actually, I'm getting some noise from Santilata.
Shantilata, you want to ask something? No, ma'am.
I think she might have raised
Okay.
by mistake or something.
Okay. Okay. So I'll go here. So here just whatever the parameters which you want. So for example, I want to compare just the amplitude of that. So I can get this, which means that the decay 2 is having the more amplitude as compared to the other one, and this the error bar is also plotted there. Okay, so with that actually you can do. So you can do these things separately also. You do this fitting for decay 1, decay 2, and decay 3. Separately, and then get the result and then plot it after that. But here with this technique, with this global fitting, you can do the thing simultaneously, okay, with the same parameter. Okay. So this is the subfitting, and then I'm going towards this. There is the 10th one. This is the peak analysis. This is again an important thing. You might have many times we have the peaks, and we want to analyze the peaks. Also, the peak fitting basically. So let me open it new folder. Then this folder two. Just open some file so that we can get an idea about the peaks. So this one, then spectroscopy, we have some their hidden peaks. Okay, so this is just some this is the peaks are there, and now I need to identify the peaks. Can anyone tell me how many peaks are there quickly?
Six.
Okay, I'll show you. There are 7 peaks. Okay, and this is the means one of the feature. Okay, you can say that I'm seeing that 8 or 9 peaks, and the origin will try to fit with those number of peaks also. Okay, so never go with that whatever the origin is finding. So analysis, the peaks, okay, and the multiple peak fit. Now multiple single peak fitting we did it. Non-linear peak fitting you have seen that the single peak. Now this is having the multiple peak. So multiple peak fit, you have to go the peaks and the multiple peak fit, and then this open dialog. Okay, now what is that? Okay, now what kind of the peak fitting you want? Okay, Gaussian or the Lorentzian. So many times people do with the Gaussian, but Gaussian, Lorentzian, Laplacian. Okay, these are the various peaks which I work, okay, on which I work and I protect the data. But you can, depending on. So as I said that before data curve fitting, you should know that whatever the curve you are going to plot it. So let me do this thing and double click. So you have to double click. So this is the 1, 2, 3. I have some small peak here, 4, 5, 6, and 7. Double click it. So it will give you have selected 7 peak. Okay, and so if you just click on the fit, then it will fit the data. If you just open anal fit, okay, so it will give you the options, and then for all the 7 peaks, first look into the graph curve. So how many how many parameters? This y naught, this full width of maxima, this is amplitude, and this is the center. So 1, 2, 3, 4 parameters. So 4 parameters for all these 7. 7 into 4 means 28 fitting parameters are there. Now, definitely, all of these would not be the same amplitude, not the same center, but they can have same full width half maxima. So they can have. So if you want to share that thing, so you can share with this thing. Where is that full width half maxima? This thing. So you can share with that, but I'm not going to that. Okay, so let's say let's fit it. It's done, and look into the quality. Now, I never seen this kind of the fitting. Never ever seen. How many nines? I'm not going to find it. Read it actually. This is the fitting of this, and this look into this fitting tolerance. 10 to the power minus 12. My God, it's one of the best fitting I have ever seen. Actually. Okay, so and this is what I have. So this is the data points. This you can get it in this particular table. Actually, all these data points, and look into that. So which means that, and this is also known as the deconvolution. So whatever the peak you have, so you have deconvoluted and you get it. So this is some sort of, you might have seen that the convolution and the deconvolution. So simple. Okay, so whatever the peak which is corresponding to here, so this is a very small peak, and you just is from the cyan color. So this peak is there. So mathematically, I can say that whatever my original curve this was here, and I just make it to some sort of peak. So this original curve is the combination of or the summation of all these small this colored 7 curves. If we just add it, then you will get this thing. So this is the peak fitting. I hope this is clear. Any doubt? Okay, no questions. Next thing is that quite important. Many times we do not see the peaks actually. So and baseline here, the baseline is very important. Is the baseline. So here the baseline is quite good. Now we will give you an idea where the baseline. You have to define the baseline also. So let me teach with this one. What's that? So this is curve. So ideally this should be one peak upward, then flat line, and then one peak downward. It should be like that. But due to some exponential function which is inbuilt there, if it is actually there, so the baseline is not a straight line, flat straight line. It is some sort of having exponential decay. So now we need to first define the baseline, then we will define the peak, and then we will do the fitting of that. So for that, again, analysis, peak, and this time we'll not go with the multiple peak, we will go with this peak analyzer, the peak analyzer. So it will analyze the peak and open dialog. So this is a window which, so in the previous version of Origin, this was not actually meant. Now in the newer version, this is more sophisticated there. So now, so my goal is to, this is the goal. Goal is what? So goal will change accordingly. So now you need to integrate a peak, you need to create only a baseline, you need to just subtract the baseline, you need only just find the peaks or fit the peaks. Basically, if you do the fit peaks, then it will do all these things. So my goal is to fit the peaks where it will integrate the peak, it will create a baseline and all this, whatever this thing they have been actually, whatever the job or the steps they have been given here. And one by one we will do this thing actually. So this is okay. Now next, so this is the baseline mode. So baseline is not a constant. The constant is given here. No baseline. This is actually defined by the user. So user will try to define. So it will actually do. It will try to find out whatever the points. So this is the point which Origin has algorithm. So you can define actually. You can define your points also. Okay. So this is actually now enable auto points. You can just disable actually. So then what will happen? You can let's say find out 10 data points for example. So it will add the 10 data points. Suppose you want to add some more data points. Okay, what you did, you add it and this double click on it here, double click on it here. So which means that now you have added 2 or 3 more data points. So they have been added. So you can modify, you can delete it. Suppose, for example, Origin due to some overlooking, it just added some point here. So baseline should not be here. So you can just remove that particular thing actually from there. Okay. So add or remove, you can just get it there. Then next. So connect by, this is the you have to fitting. Okay. Just go back to there somewhere. So let's say I want to add. So this was done actually. Next. This one fitting is done. Now snap to this particular spectrum. Okay, so which means that whatever the points you have defined in this red points you have defined, so whatever the close point to that, close to that, it will always look into that whether the points this is of the baseline or of your actual spectrum, of your baseline or of your spectrum. Now the fitting, whatever the fitting function you want to have. So let me say this is my fitting function. This is what my so next. So that's just base. If you want to subtract it, then baseline would be subtracted, but I do not want to be baseline to be subtracted. Okay. It will find it, how many peaks are there. If not, then you can define it. You can add the number of peaks also. Okay, just like the previous one. And the method for the peak fitting, it must be there. Yeah, here. Local maxima or the second derivative. The second derivative method or the first derivative method, they have been used when you have the peak which is very close to each other or the overlapping peaks are there. Then this would be actually there because you can get the more variation in using the derivative option. Okay, and so here I am going with only this was local maxima, but let's say you can do with that, so it doesn't matter. Okay, so this turn. Method is weighting average. You can do peaks. You can add it, add some extra basically peaks. Now, one important thing is that when you do this second derivative, this is an important thing is there. Then this smoothing factor is also activated. So you can smooth because if somewhere you have the nearby two data points, then that two data points is due to your experimental feature or just a data fluctuation. Data fluctuation is there. So one can identify that, and one can even apply some filters, some methods to filtering out or to smooth that particular data points also. So here actually I'm not going with that. Let me go for this. So let me do it. Let me quickly finish it. That so many data points are there. Let's finish it. So it's there. So this is the curve. You can see the green color is the baseline and the red color is the fitting of that particular data point. So and the fit parameter. So let me double click on it. Workbook. This is the workbook, and this is the fitting parameters which are given here. Peak, position, base. So both the peak. There are two peaks. The two peaks they have been fitted with the Gaussian. Their integrated area, their center. Their maximum height, their full width, half maximum, everything has been given. And this is the data for the baseline. So you will just see baseline is like that, exponential decay. Okay. So everything is just, you can just get it from this particular thing. So this is actually just a simple, I would say that the fitting of this thing. Suppose, let's say, I would like to do more analysis, not more, just here. Analysis, nonlinear curve fit. Where is the nonlinear fitting? Nonlinear curve fit, open dialog, and the function is not given, and you want to add some new function. So what I'll do, I have some user-defined function, and let's say I create a new function. Any other function, let's say I would like to name it at STTP 2021. Okay, some function. It is explicit or implicit, you need to define. So most of the time we work with explicit function. Expressions, I would like only expressions. Then let's say x and y and the number of variable, let's say a, b, and sorry, a, b, c. These are the three variables. Okay, these are the actually the parameters. Derived thing, you are not getting anything. Constant, you are actually not defining anything. And you can, if you have, then you can define it. And let's say the function. So let's say I have a means y is equals to a into x square by 2 plus the the whatever a b c small or capital I have written there, then I have to use those only. X, okay, minus ln x and then multiplied by c. Okay, so I can let's say initial values is there. I need to check whether this is working. Yeah, so it's working. It gives me a value of y equal to 1.5. So this is what I have. And let's say next I can define upper and lower bound there and finish it. So now the graph is fixed. Okay, and this is the graph is there. So now I am fitting that data, that equation, the data which is there with this this equation. So this is what there. So now this is the fitting of that particular data. Okay, so this red is my equation, the fitting data, and this black one is my actual data. Okay, and definitely this is my random function, so it is not fitting that much. So you can define your formula, your expression, and this is not will be given because this is given by us. And look into this, the COD R square value is very, very poor, 0.8. Okay, so with that actually also means you can define your function, your thing, and you can go ahead with that thing. One last feature that is the statistics and where is analysis. Mathematics is there, yeah. Interpolation and extrapolation. This is there. So I just put it there. Uh, First of all, I need to there is select both x and y, and then interpolation. The values to be interpolated. Linear, one could be new. Okay, so no, it's it no it, it let me delete it again. I should get some dialog box. No, this is yeah. Interpolate and extrapolate. Open dialog. This is yeah. So let's say this curve starts from 10 to somewhere actually 10 to 355. Okay. Now I need to go with that. No, not from 10. Go start with 1 and go to the let's say 10,000. Not 10,000. Let's say 500 for example. And here this is at an interval of 1. No, I said that let's go with the at an interval of 2 only. Okay. So 2 means that 251 data points like that. Okay. So I did it with like and then. So this is the curve which I have. So now the new value is there. Okay. Now let's see whether the graph shape and all those things they have been changed or not. So it should not change. It should not change. So let me, this is both are actually dependent. So you just see there is a you are not getting any difference between black and red. Okay, so they're exactly overlapping. Even if I zoom into the peak also, and it should yeah. So there is some variation is there. So red is actually now that is at an interval of 2, and black one was at an interval of 1, which means that technically the smaller the step size, you will get the better quality of the data. Basically, my point was that one can actually generate the more data points. Okay, but you should not do it for the generating your data for the research point of view. But this is for the actually fitting purpose. Okay. So this is the data interpretation. I can do this with data smoothing also. So if I have this thing, then analysis. Then again I have mathematics. Somewhere I have a smoothing. Signal processing. Then this is smoothing. So data smoothing is there, so you can smooth the data. So data is right. Okay. So I will take some time for the system analysis because so far. If any more thing which is specific font, then you can explain specifically, then we can have and we can get for that and we can get that. So with this, I just stop here, and I would like to take some question so far. The Fourier transformation can also be done actually. One thing, yeah, this is the Fourier transformation. So it's a quite simple thing. Just you need to add some data. So maybe I have FFT somewhere you can find. Gadgets, you can see, yeah, this is the gadgets. Yeah, gadgets are here. So actually, this is a data I have. So you can just plot it. So, and this analysis, signal processing, and the field FFT. FFT. So this is what you have for your transform of that. Okay, so you can just check it. Where is the Fourier transformation? How many peaks are there? Fourier FFT transformation can also be done. Okay. So now, any question? Think if you want to discuss, I can take.
Sir, there is one question. I think Ayushi.
And
Hello, sir. Am I audible?
Yes. Yeah, clear.
Sir, would you please give some brief idea about contour plotting and especially in that heat map?
Heat map. So for the heat map, actually, I do not have that particular data. So if you just plot that, I mean, I just said that this is some sort of more specific, and if we have that kind of the data, then only we can plot it. Okay, I just said that. Okay. So if you can share that data, then I can work on that and then give you the heat map of that. Because for that you need to have the time also, time how the temperature is being changed as a function of time, and then we can plot it as a heat map, the red color and the blue color kind of thing. This is what you are asking, I think, red and blue. These people usually plot the that actually, the cooling and the heating thing as a function of time at different aspects. So you can just email me, then I can just prepare some slide or video, and then I can give it back to you. Okay, because I do not have that particular data, and this is some sort of or I will put it in this whatever the WhatsApp group the organizer has created. So I will create that thing with you, and then you will get that. Okay. So any other question?
So I think if there are no questions, I would like to thank Dr. Himanshu Pandey sir for this wonderful lecture, and it has been really helpful for all of us, like yesterday's session as well as today's. So we are very much thankful to you, sir.
Thank you, Charlie. Nice words.
Okay, so I think we all can have a few minutes break before Vipul sir joins in. So let's have 2-3 minutes break, I think.